So from last time, given a reaction with delta G minus, therefore it's spontaneous, therefore it will happen eventually. Okay? You get one of these free energy diagram thingies that I've been drawing. Oops, sorry. High and low, free energy. And if you have some state, thinks I'm crossing it out, A, and you have some state B, so that reaction is spontaneous, energetically downhill. We talked a little tiny bit about something in the middle, about rate. There'll be some state A, B, some sort of intermediate in between. This thing, let me label these in different colors, make it a little bit clearer. This thing is called the transition state. To give a formal name to that intermediate. It's what it was if we were talking about the snap bracelets. You had sort of one state was straight, another state was coiled, and that transition state in the middle was that little kink you put in, right, that started it all. So this transition state is an intermediate between A and B, right? So, for example, if one state is me bonded here with a weak bond, and another state is me bonded here with a strong bond, there's some intermediate where, like, I'm partly breaking this one, just starting to make that one on my way over, or going either way. There's something in between. And that transition state turns out to be key in thinking about the rate. And so, if you have this pathway, then this energy here, talked about a little bit before, is the activation energy, EA, and it determines the rate. That is basically the molecules of A with energy greater than EA, with more energy than the activation energy, react to form B, whereas molecules of A with energy less than EA, oh, I'm sorry, I put it this way. The other ones don't, that's obvious. And so, therefore, more A's with energy greater than EA leads to a faster reaction. That's a general principle. So basically, you've got to get over that barrier. So there's molecules of A, and they have a whole bunch of different energies at room temperature. Any molecule of A with activation energy or higher can make it over the hill and react. The ones that don't sort of jiggle around and stay as A. All right? Once you get over the hill, you're going to go all the way down to B because it gives you more energy back than you put in. All right? So you might ask, how do you control so how to speed the reaction? There's two ways. And why does it matter? Because, again, living things, I want to digest my lunch sometime today. And so it needs to happen relatively quickly. And so there are two ways to make reactions happen faster. A is to heat it. And what that does is that leads to higher average energy. That is, you raise energy. Therefore, more molecules with energy greater than activation energy. That is a faster rate. If you like, this is like saying jump higher. That is, if you want to get over the bar, if there's some bar the molecules have to get over, some energy bar, you can either jump higher, right? So more of them If you jump more vigorously, more of them are going to have energy to get over, so you can jump higher. Heating is one way to do it. So if you heat it up, more molecules have enough energy to make it over the top. The other way to make the reaction go faster is to change the reaction path, to lower the activation energy. It has the same consequence. Therefore, more molecules with energy greater than the activation energy. Therefore, a faster rate. This is like lowering the bar. All right? And this is catalysis. All right? So in living things, if you want to digest your lungs faster, you could just heat it up. Right? Cooking it actually helps to break down the proteins faster. The problem is you can't heat yourself up that hot or you'll cook yourself. So heating things up is not a solution for living things. Catalysts, finding a cheat, making a way to make the reaction easier, lowering that activation barrier, basically facilitating this reaction, makes it happen faster. More molecules have enough energy.